This video is to demonstrate that 5-column, left to right, top to bottom structure for solving problems in spreadsheets from the ground up. So we're going to build a solution to this relatively simple problem over here. It's a little bit tedious to watch me type while I'm talking, but that way you get the full exposure to how to use this structure to improve your ability to solve problems and to communicate your solution to such problems. So first, the problem. Here's a free body diagram of a cylinder piston. It's a hydraulic cylinder that has pressures on each side of that piston. There's an area, differential area on each side, and then there's an external force. The question is, how much force can a cylinder with 75 millimeter diameter and a 25 centimeter rod exert when extending if the supply pressure is 20 megapascals and the return line pressure is 2 megapascals. So we're going to work up this solution starting in this 5-column format where all the inputs are gathered in one place, will flow into intermediate calculations and eventually outputs. So I can sort of start simply by identifying that one of the inputs is the diameter of the cylinder, which it happens to be 75 millimeters. And it's also known as the bore of the cylinder. I would have the diameter of the rod, which in this case is 25 millimeters. I have a pressure on one end. I'm just going to call it P1. That's what it looks like in the diagram. The reason I need to put the P_1 is there is a cell over here. Scroll right just a little bit. There is a cell that's P1. So I can't just put P1 because that would refer to that particular spreadsheet cell. So this is the pressure on the head end of the cylinder, and in this case it's 20 megapascals. When I do that in Excel, it automatically uncapitalizes my P. Since it's named after Pascal, I must capitalize it. So then we have P_2, like pressure 2. So this is the pressure on the rod side of the cylinder. That's 2 megapascals. So those are my inputs. I'm going to jump down to the outputs, and what I'm looking for is the external force when extending. And let's see, I'm in metric units, so I'm probably expecting that to be newtons. So I'll just put that there, and now I'll think about the problem. I haven't done any calculations yet. I've just simply echoed the problem statement. These are the things I know. This is the thing I'm looking for. Now I need to fill in the solution. So I recognize that if I sum the forces on that piston assembly, I've got P1A1 pushing it to the right, P2A2 pushing it to the left, the external force pushing it to the left. So if I want to solve for external force, I do the simple little algebra down here. But realizing that A is the area, and I was given diameters, that's why I need the formula for the area of a circle. So that makes me think maybe a couple of the intermediate calculations are I need area 1, area on the cap end or head end of the cylinder. And then I also will need A2, which is the area on the rod end of the cylinder. Now if I don't have the drawing here, but on the rod side, this A2 is actually A1 minus the area of the rod. We'll get to that in a bit. All right, so since I have millimeters as diameter, I'm expecting millimeters, square millimeters. I could use mm and put the superscript 2, but this will suffice. These are going to be square millimeters as units. I'm going to make a little note here just for all of us to keep track of, and that is that 1 megapascal is equal to 10 to the 6th newtons per square millimeter. Newtons per square meter, sorry, which is the same as 1 Newton per square millimeter. All right, so let's fix that capitalization. So just remembering that so I can deal with my units as I solve this. All right, so what's the area of the cap end of the cylinder? I could simply enter it's equal to pi time, and the function for pi in Excel is pi parentheses, so that will give me pi just to prove it. There it is, 3.14159 and more digits. So I take pi times radius squared or diameter divided by 2 squared. Now, most conventionally, a person would put in here C3 divided by 2 and square it. And that works. It gives, it's got too many digits, let's fix that. That works, but I'm going to tax myself and anybody else who reads this spreadsheet to remember what is in C3. So this is a big step in the power of this structure for solving problems. I'm going to delete that. I'm going to highlight the whole sheet, which is this little triangle between the A and the 1. I will go to formulas, and there is in the middle a name manager. I can create names from a selection, and because I have the names that I want to use in the left column, I choose the left column and hit OK. Now from this point forward, if I want to talk about the diameter of the cylinder, which is in row 3, I can use the name D sub sil. So let's try it. So it's pi times the diameter of the cylinder. Now, it depends on the version of Excel that you have, but here in the latest version that I have, I need to use the @ sign before my names, otherwise I get a spell error. If you get the error @ spill, then you simply know I need to put the @ sign. So D sub cylinder, divided by 2 to get the radius, and then square it, and it computes. So how about the area on the rod end? Well, that's going to be the area on the cap end minus the area of the rod, which would be, again, pi times that diameter, which is d at d sub rod, divided by 2 squared. And then I'll close that other parenthesis. So does that make sense? I'm going to take the area on the cap end and subtract the area of the rod, and the area of the rod is pi d squared over 4, d over 2 squared. So there I go. Still too many digits. Let's fix that. So I've got the 2 areas. So now, to do the force balance, I'm simply looking at the equation over here. The external force is, if I do the algebra, P1A1 minus P2A2. So I'll go down here and equal at P1 minus times A1 minus P2 times A2. So in this case, the algebra is very straightforward. Like, it would take less time to actually solve this on paper than on spreadsheet. But on purpose, I've chosen a simple problem to illustrate the structure here. So then I get an answer of a whole big number of units. So then in this case, I would often do something like this. I will calculate the same thing in different units. Hence my silly little subscript of du. And if I wanted this in kilonewtons, for example, then I would take, it's the external force divided by 1,000, and I will get that. Now, why did I get the hashtag name there? Oh, I mistyped it. It's F sub EXT, and that fixes it, so I get my answer in kilonewtons. The one last thing that we will do in this short demo is copy all of these formulas from column C. I'm going to paste them in column E. But in column E, I don't want them to actually be computing. I want it to be the notes that explain the calculations. So while highlighted in column E, I'm going to go to the home ribbon and edit and replace. The shortcut is Control H, but I'm going to replace every equal sign with simply a single quote and an equal sign, and I'm going to replace them all. It made 4 replacements, close that, and now in my spreadsheet, these cells explain what's going on over here. Of course, if I have the digital version of the spreadsheet, I can move my cursor and see in the formula bar what the formula is. But the beauty of having them echoed is now without scrolling, and if you happen to have the printed version of this, you have a complete audit of all of the formulas in the spreadsheet in one view. So it flows from top to bottom, all the formulas are shown, the variable names are defined, and it reads like math, rather than cell references of C3, C4, C5, and C6. It's easy to follow because the math of the code matches the math of the diagram or whatever it is that you would have written in paper. Again, I'm Dennis Buckmaster, a professor of agricultural and biological engineering at Purdue University. I've been teaching this structure for problem solving for a long, long time. It's time-tested and true and very effective in communicating your solution to mathematical problems.